Hi guys, Mr. Roth here, and today we're going to be learning how to solve rational inequalities. We're given a rational function, told that it's not equal to something, and we want to find all the values of x that we can plug in that will satisfy this inequality. So let's remember our first step is always to get 0 on one side of the inequality. Well, that's not too bad. We'll subtract 2 from both sides, giving us x over x plus 2 minus that 2 is greater than or equal to 0. Now, we don't like having these two separate terms on the left side of the inequality, so we need to find a common denominator. The common denominator, of course, is x plus 2. So our right term here, we're just going to multiply by 1 in the form of x plus 2 over x plus 2. There's our 2. Now let's see if we can distribute this negative 2, combine some like terms, and maybe get a simpler inequality. Combining our numerators, we get x minus 2x plus 2. We found our common denominator, so we can combine them. And finally, combining like terms, we find negative 2 times 2 is actually negative 4. Combining like terms, we get negative x minus 4 divided by x plus 2 is greater than or equal to 0. And personally, I like to always have a positive coefficient on my x, so I'm going to go ahead and factor a negative sign out of that numerator. So it becomes negative x plus 4 divided by x plus 2 greater than or equal to 0. Now at this point, it's easy to identify the zeros of my numerator, which are zeros of the rational function, and my zeros of the denominator, which are where asymptotes will occur. Right? We can't have a 0 in the denominator, but we can still use it as a boundary value when creating our sign line. So we'll draw a line. We'll label our boundary values. One of them is negative 4, our 0 from the numerator. Another is negative 2, a 0 from the denominator. And let's see, we want our rational function to be greater than or equal to 0. So it's okay for x to be equal to negative 4, because that's a 0 of the function. We'll draw a point, a closed, filled-in point over negative 4. However, it's not okay for x to be equal to negative 2, because that would lead to a 0 in the denominator, which of course is undefined. So we draw an open point around negative 2. Finally, let's apply the sign test to see where this is positive, in other words, greater than 0, and for which values of x this is negative, less than 0. We could pick any value of x to plug in. Let's just go with 0 because that's an easy one. If x is 0, then we get that negative 4 over 2 greater than or equal to 0. So negative 2, is that actually greater than or equal to 0? Well, no, of course it's not. So when x is equal to 0, in other words greater than negative 2, our rational function is negative. Because the multiplicity of each of these zeros is 1, an odd number, we know that the sign is going to change at each of our boundary values. And now we can see, okay, the function is positive when x is between negative 4 and negative 2, including negative 4 but not negative 2. So that's our solution set. To express that as an interval, well, our lower bound is negative 4, and it's included, so we use a bracket. Our upper bound is negative 2, and it's not included, so we use a soft parentheses. And if you like to be fancy, you can write that x is an element of this interval. Thanks for listening.